Skill 4 is the last lesson in this unit, and even though it's not a lot of skills, it's probably the heaviest thing that you guys do, as far as there isn't really a memorizing procedure, that you guys have to be a little more creative with these identities to really see what's happening. So make sure you're getting a lot of practice trying things in order to try and figure out what's happening in each problem. So today's goal is to be solving. So our goal is going to be to simplify to a point where we can solve. So a little bit of review. If we're trying to solve something, I don't know, like this, if x just shows up in multiple places, we try to combine all of the x's together. So one idea is to gather all the like terms on one side that contain x. But then also remember your quadratics. If I have something like this, I don't then try to get x alone. I try to get all the terms on one side, and I look to factor or solve the quadratic formula. So the reason I point that out is if you see something, just gonna try and, if you guys see something like this, this is a quadratic because there's something being squared plus 3 times something plus 2. When that's an x, you guys are really comfortable saying that's x plus 2 times x plus 1. The only difference now is it's not an x. It's a cosine of x that's in these spots that you would then be using in these spots as well. Okay, so I just want you to see that parallel, that you might not be used to seeing it exactly this way, but you have seen this structure before, and it's okay to think about it like that. So I'm going to look at our first problem, sine squared x plus cosine 2x minus cosine x. So there's a big issue with this problem. Number one, there's sines and cosines. Number two, this one has a double angle while these ones have single angles. So my goal is going to be to change all of them to have single angles. So like I don't want this to say 2x inside the angle. So I want to refer back to my double angle identities and think about ways that I could change that cosine of 2x. The other thing is, if these are all cosines, I would like this one to be a cosine as well. I know this one could be written in terms of cosines, sines, or both. But this one can't be really changed easily. There's no identity for just plain cosine. So that's going to kind of dictate that I'm going to try to change all these other things to something in terms of cosines. So if you can kind of see where I'm going. I don't want a 2x in the problem. I want all x's. I'm choosing to try and change everything to cosines because I don't really have an identity to work with this. So I want things to be similar to that term. So how to change things to cosines? Sine squared. If we use our Pythagorean identities, sine squared can be rewritten as 1 minus cosine squared x. Okay. Cosine 2x, if we look at our double identities, the cosine was the one that could be written several different ways. If we're trying to rewrite it just with cosines, it can be replaced with 2 cosine squared x minus 1. Then we have the cosine x that we don't have an identity for, and that's set equal to 0. So now I'm going to look to take out these parentheses, since it's addition, pretty good here. And I'm going to look to combine like terms, one, and see what we really have here. So squared wise, here's a cosine squared x, here's a cosine squared x. So that's like having, you guys, a minus x squared plus a 2x squared. And those would combine together to be x squared. So I'm thinking about that as combining together to be a cosine squared. I then have a cosine x. There's no other single powers of cosine, so that can't be combined or simplified with anything. I then have a positive 1 and a negative 1, which will add up to 0 and cancel each other out. So again, if you're struggling with the cosine part of it, what you have right here is really similar to having this. That's a quadratic. I'm going to solve by factoring, and in this case, factoring would mean taking out the greatest common factor, which would be a cosine of x. And just like before, we factor when it's set equal to 0 because then we know that one of the factors has to be equal to 0. So cosine x could equal 0, or cosine x minus 1 could equal 0, which tells me cosine of x would equal to 1. And I want you to think about your inverse trig functions in this case and try to think about where this would occur. So first, and then as we're doing that, the restrictions here aren't the same as the inverse because the problem listed a restriction. They want us to look at the whole unit circle from 0 to 360. So here, I'm going to think about where would the cosine be equal to 0 in one entire lap around the unit circle. So cosine is the x-coordinate. The x-coordinate would be equal to 0 here. Sorry, let me do that in a different color. So it would be equal to 0 here, as well as here. And then where would the cosine be equal to 1 around the unit circle would be here. Now, this angle here, I would call 90, because that's what it would be called if we're looking just between 0 to 360. So at 90, this one would be 270. And this one, I'm going to call 0. The reason I'm not calling it 360 is look at those boundaries again. It does not say I can be equal to 360, but it does say I could be equal to 0. So my answer here is that x could be 0 degrees, 90 degrees, or 270 degrees. So a couple more here for you guys to get exposed to this idea. Now this one, notice that there's no other signs. They're all packaged right here. That one you don't have to approach from a factoring perspective. You could isolate the sign in that case. So you could divide by 4. And you'd have sine squared x equals 1/4. You can square root both sides, and just be careful when you do that. That means you would get plus or minus 1/2. So you want to think about all of the places in one lap around the circle, because we're still in this restricted 0 to 360 is where our answers should be. One lap around the unit circle, which angles between 0 and 360 make the sine equal to 1/2 or negative 1/2. So here's 0. I'm going to start going around the circle. Right here at 30 degrees, you have a y value of 1/2, so the sine would be equal to 1/2. So 30 degrees is 1. The next time we would hit 1 is over here at 150 degrees. It also has a sine of 1/2. Next would be here at 210 degrees. That has a sine of negative 1/2. And then finally over here at 330 degrees. So there's 4 angles that could have that sine. So those 4 angles would be our solution for this problem. And then for part B, it's tempting here to see sine x on both sides and maybe want to do something like divide by sine x, but we shouldn't divide by sine x because we don't know its value, and by taking it out of the problem, you're taking out possible solutions. So because it exists on both sides, and especially because on this side it's combined with a cosine x, these aren't like terms, but they're also not squared, so we can't substitute anything in. So first bring them to one side together so we can see what we can do. And you know what? We can actually still factor this because these two terms both have a sine x, and when we factor out the sine x, what's left is 1 plus cosine x, and individually we can set those both equal to 0 and get our solutions for that. So we're looking for places where sine x equals 0, and to finish this one, it would be places where cosine x is equal to negative 1. So where sine x would equal to 0, Sine is like the y coordinate, so there would be a 0 here at 0 degrees, as well as here at 180 degrees. And cosine would be equal to -1 at 180 degrees. So there's just two solutions here, 0 and 180 degrees. Okay, so example 2, the equation part of it is actually quite simple. You really would just have to subtract 1, and you have where is cosine theta equal to -1. And if we were still dealing with the 0 to 360 situation, that happens at one position over here at 180. That's where you get a cosine of -1. But notice how the directions have changed. We're not finding just the angle from 0 to 360. We're actually finding all the angles in radians. So that would mean any angle that lands here. And since you can keep adding or subtracting 360 and get coterminal angles, there are infinitely many of them. Okay? So what we're going to do here is going to seem familiar to how we wrote the range for our step functions way back in the beginning of our course. And in the last unit, how we wrote portions of our domain, or where the asymptotes were occurring, for our tangent functions, that we have this idea of where there's a starting point and then how far you have to go before you land on yet another one of those. So what we want to say is the answer is 180 and all angles coterminal with 180. So the way to say that is to say 180 plus, so 180 is one answer. We want to know how far apart it is from other answers. You have to do an entire lap around the circle. So that would be 360. And that could be done as many times as you wanted. So that's why it gets the K. So again, kind of a starting point, a place where you know this is occurring. And then how far apart these are, but since they can happen many times, it's K. Now this specifically wanted it in radians. So everything I just said there is like in degree speak. Kind of. So in radians, this would be pi plus 2 pi k. And then we want to make sure we add that statement where we say where k is an integer, because otherwise people won't understand exactly what that is. Now we're saying that we understand they could plug in any positive or negative whole numbers for k. And when they did that, they would still land at a place where we have a solution. So the focus here wasn't really on the equation part. If you guys understood example 1, you were probably fine with that. But it was more like, do you understand how to find all values, which is this equation perspective here for writing your answer. And this one used radians instead of degrees. So here's a couple of examples. So the first one, it says cosine 2 theta. That can get pretty tricky. So if you can solve it by substituting out, that would be my suggestion for you. So let's say I decide to change cosine 2 theta into this identity. Then that simplifies to say 2 cosine squared theta minus 2 equals 0. Because all the cosines are in this one term, I don't have to try and like factor like a quadratic. I can just isolate the cosine. So I would add 2 to the other side and then divide by 2. And then my last step here would be to square root, and I would get cosine of theta equals plus or minus 1. And my thoughts would be about where on the circle. I first focus on 1 time. Where does the cosine equal positive or -1? And that would be at 0 or 180. Then I look back at the directions. This is all values of theta. It is in degrees, so I can keep using degrees. So the best way to write this, even though there's 2 solutions, I can write them together in one equation because they are exactly the same distance apart in both directions. So to get from 0 to 180 in either direction, you can go 180 degrees that way or this way. And to get from 180 to 0, you could go 180 degrees that way or that way. So because they are separated by the exact same amount in each direction, I can combine their answer into one answer. And the way I would say it is that the answer is, pick one of them as a starting point. I'm going to pick 0. Plus, instead of saying 360k here, that would take me back to 0. I just want to go over to 180 to this other side of the circle. So I would say plus 180k. So that simplifies to just be 180k. And again, I make sure to say where k is an integer. Okay, now looking at part B, again, all the cosines are here. It's almost isolated, so I'm just going to divide by 2. So I have cosine of theta equals rad 3 over 2. So think about your unit circle. Where does the cosine of theta equal positive rad 3 over 2? So cosine is the x-coordinate. The x-coordinate is rad 3 over 2 at 30 degrees, as well as 330 degrees. Now, to me, this instance is different than the one we talked about previously in part A. I cannot write these two answers as one equation because from 330 to 30 degrees this way is only 60 degrees, but to go from 30 all the way back around to 330 is 300 degrees. Since they're not separated by equal amounts in both directions, I do need to write each answer separately. So first I'm going to focus on this first one, 30. So my answer there, remember I'm trying to write every possible angle that would land at the same position as 30. So I start with one measurement that I know is there, which is 30. Then I add to it the amounts that would take me to land on the next one, back at this same position, which would be an entire lap around the circle. But the k goes with that because you can do that entire lap in either direction or as many times as you want and still land on that position. The other option, there's a second solution here since these are not connected by the same amount of difference, is at 330. And again, you would have to go around the entire circle and land back at that same position and be coterminal to it in order to list the infinitely many answers at that position. So it's these two things. And again, we want to list where k is an integer so people understand how we're using that value. Lastly, I'm going to look here at part C. For part C, again, all the cosines are contained right here, so I'm not going to focus as much on factoring as I am on getting the cosine squared alone. So I'll add 1 to both sides first, then I'll divide by 2, and then I'm going to square root both sides. So I'm going to include plus or minus. The square root of 1/2, if we simplify it using our radicals and rationalize the denominator, we get plus or minus rad 2 over 2. So as I think about these positions, where is the cosine on the unit circle equal to positive or negative rad 2 over 2? I immediately think 45s, and because it can be positive or negative, this is actually happening at each 45. So at 45, at 135, at 215, 225, and at 315. So at these 4 positions. Now, notice that all of these angles, if I go from 45 to 135, that's a difference of 90. 135 to 225 is 90. 225 to 315 is 90, and 315 to 45 is 90. They are all separated equal distance, more like in this first example. That means I can write them all together as one solution instead of having to write like 4 different solutions. So you need to pick a starting point, so it can be any one of these or anything else that would land on any one of these. So I'm just going to pick 45. That's my starting point to guarantee I'm sitting on a 0. Then I add to that the amount of degrees that would carry me to a next 0, which in this case would be 90 since they're all 90 apart. And that's what gets the k, because you can go 90 degrees as many times as you want from that starting point and you'll continuously land on yet another solution. Okay? But again, we have to make sure we specify that k is an integer so somebody's not using a fraction of the 360 or something like that. So as we look at example 3, we're going to go ahead and solve it, but a little bit of a struggle here. I see sine squared minus 1 on one side. I see cosine squared on the other side. Remember, in order to solve it, I either want to be able to isolate one trig function or get everything together and kind of treat it like a quadratic. I see the squareds here, but I don't like that I have sines and cosines with no relationship. So I'm going to try and substitute one in. So according to our Pythagorean identity, cosine squared could be written as 1 minus sine squared. So I'm substituting that in for cosine squared. It's changed to 1 minus sine squared. Now I'm going to try and collect like terms. So I'm going to add 1 to both sides. So I'd have sine squared x equals 2 minus sine squared x. And then I'm going to move the sine squareds together on the same side, because remember, that's like having x squareds. They are like terms. So here's what I would have. I would then divide both sides by 2. So I have sine squared x equals 1. And if I finish by square rooting that, I would have that sine of x equals plus or minus 1. So again, think about positions, angles on the unit circle. Think once around first. Where would sine equal positive or negative 1? That would either be at 90 or at 270. When I look at the problem, it's all values, so I need to make sure I'm including that infinite list through that equation, and it does have degrees. And again here, I can write them all as one equation rather than two separate solutions, because these two solutions are equal distance from each other on both sides. So that means that I can combine them together, just making sure I account for that distance. So my answer here would be that the angle could be equal to, pick one of the places that you know could be a starting point, so say 90, plus how far is it to the next solution since they're equal distance apart. In this case is 180. And then the k goes with 180 because you could jump 180 one time or 2 times or 3 times or negative 3 times from 90 and still land on a solution. Again, we have to specify that k is an integer. So when we look at the first try this, you might not like the way it looks, but actually, I'm not going to switch anything out of here, and here's why. It's set up like a quadratic. See, the thetas don't have any 2's in front of them. They're not double angles or anything like that, so that's good. And this function that I can't really do anything with is a cosine. This one's also a cosine. It just happens to be squared. So remember, what you have here is like having 2x squared minus 3x minus 2 equals 0. If you were factoring this, let's set it up. Here's what I would get. That applies here as well. It's just that instead of 2x, it's 2 cosine theta plus 1. And then the other factor is cosine theta minus 2. And just like we would if we were using these, we'd set each factor equal to 0. So that's what I'm going to do over here. So I would get that cosine of theta could equal negative 1/2, or cosine of theta could equal 2. 2 is not possible. Remember, the cosine's highest value is 1 because it's the ratio of the x value over the radius, and the greatest value of the x value would be the same as the radius. There's no way it could ever exceed 1. So that's not a possibility. So I'm only going to look for these solutions where cosine of theta would equal -1/2. So I'm going to think about where those would be on the circle. So cosine equal to -1/2 would happen at 60, sorry, that's not 60. It's a reference of 60, but 120 and 240. Then I'm going to look back at the directions. My angle is supposed to be between 0 and 2 pi. Given that the parameters are in radians, I should be using radians. And given that it's only from 0 to 2 pi, I shouldn't be listing those equations with k. I should just list the couple of times that this occurs. So 120 in terms of radians is 2 pi over 3, and 240 in terms of radians is 4 pi over 3. So I have two solutions for the angle in radians between 0 and 2 pi would be 2 pi over 3 and 4 pi over 3. Example 4 is super similar. Again, I'm going to point out those similarities to you. Notice that there's a lot going on in the equation, but that the angles are all just singular angles, so that's good. That a sine function that's not being squared is where I can't really do anything with it. So I know that that's going to stay, but that's okay because this is sine squared. So again, the way that I'm thinking about this is like I have 2x squared minus 3x minus 2. And again, how would that factor? The exact same way. So that's exactly what I'm thinking about here, except for it's not x, it's sine theta. So I'm going to set these equal to 0, each factor separately. And so my two equations state that sine theta could be equal to -1/2, or sine theta could be equal to 2. And again, the sine theta being equal to 2 is not possible. Just like the cosine, it has that maximum ratio value of 1. So that's an impossible circumstance. So I'm just going to look for places where the sine would be equal to -1/2. So in one lap around the circle, just thinking about that, the sine would be -1/2 here and here. I don't need to go to infinitely many solutions. It specifically has it between 0 and 2 pi, but I should name them in radians given as what they are there. So in radians, this is 7 pi over 6, and this is 11 pi over 6. So my angle value in radians between 0 and 2 pi would be 7 pi over 6 and 11 pi over 6. The first try this here is a little bit frustrating. I mean, it looks so simple, but actually this is really difficult. And the reason that this problem is really difficult is because none of the cosines or sines here are squared. So we can't substitute anything in. So you know what I'm going to do? I'm going to actually go ahead and square both sides. Now, some of you might not think that's okay, but remember, what we're doing in this lesson is really different from what we were doing when we're proving. When we're proving, we can't do things to both sides of the equation because we're supposed to prove that they are equal to each other. In solving, they're telling us these two things are equal and to find out when it happens. So we have a little more freedom to do what we want to both sides of the equation. So this would become cosine squared. And then when you square the sine quantities on the right side, remember you have to like FOIL or distribute out that. So we get this. Now, this gives me some direction. I want everything written in terms of sine because this guy right here doesn't have anything to substitute in still. So he's going to have to remain a sine. So I would like this to be changed into sines, and according to my Pythagorean identity, I can change that to 1 minus sine squared theta. Now, because it looks like a quadratic, I'm going to cancel everything from this left side by doing its opposite operation, and then do the same thing on the right side to see if I can come up with a quadratic that I can factor. So here's my quadratic, and it is factorable. So I would factor that by removing the greatest common factor, which is the sine. Oh, it's 2 times the sine. And that would leave me with 1 plus sine theta. So I'm going to set 2 sine theta equal to 0 and 1 plus sine theta equal to 0. So this would say sine theta equals 0. This would say sine theta equals -1. So I'm going to think about where those things would occur. So where does sine theta equal 0? It equals 0 at 0 as well as at 180. And where does it equal -1 at 270? And I'm only going to look one time around the circle because the parameters are in degrees and they're just from 0 to 360. And so I'm just going to list these 3 angles. My theta could equal 0, 180, or 270. And for these ones, you might just want to double check because you did square the equation, and when you square it, sometimes you lose track. So because we squared the equation, it could have made extraneous solutions. So let's just double check. When we plug in 0, cosine of 0, does it equal 1 plus sine of 0? So cosine of 0 is 1. Sine of 0 is 0. 1 does equal 1 plus 0. Let's test 180. So cosine of 180 and 1 plus sine of 180. So cosine of 180 is -1. Sine of 180 is 0. This actually doesn't work. So 180 is actually extraneous. And now I'm going to check 270. So cosine of 270, does it equal 1 plus sine of 270? So cosine of 270 is 0. 1 plus -1 is 0. That works. Okay. So again, why did I check this one and not other ones? I only check when I'm dealing with something that could have been extraneous. And when I square both sides, I could have taken something that was negative on the right side and positive on the left side, and they'll look equal when they're squared when they weren't actually equal to begin with. So squaring both sides here was my key to check. In example 5, sorry about that. Again, when I look at it, notice that nothing is squared. So I'm going to go ahead and I'm going to square both sides again. And again, I can do this because we're solving. I couldn't do this if we were trying to prove 2 things equal. So if you take this and FOIL it out, stuff like that, get this. And again, in this problem, I want everything to be cosines because this guy doesn't have an identity to change. So I'd like everything to be in terms of cosines to work with that. So I'm going to use the Pythagorean identity to substitute sine squared to 1 minus cosine squared. And then I'm going to bring everything to one side just like I did before in the previous example. These ones are really similar. These cancel out. So I have 2 times cosine x is cosine squared x. And I'm again going to factor. So the greatest common factor here is 2 cosine x. And that leaves 1 plus cosine x. And I'm sorry, I'm going through this one a little bit quicker because this one's, all these steps are exactly the same as the one we did before. But if you have questions, definitely message me and ask. So this becomes cosine x equals 0. This becomes cosine of x equals -1. When we look at where this occurs, cosine equals 0 at 90 and at 270, and the cosine equals -1 at 180. So my inclination is to say all of these. However, just like the last problem that we tried, I'm going to check because I did square both sides again, which could have created Like if I say 4 equals negative 4, we all know that's not true. But if I square both sides, it says 16 equals 16, which is true. So squaring both sides creates possibly some extra solutions. So as I look, I'm going to plug in and test in the original version of the equation. So does sine of 90 equal 1 plus cosine of 90? So sine of 90 is 1. Cosine of 90 is 0. That works. Now I'm going to test 180. Does sine of 180 equal 1 plus cosine of 180? So sine of 180 is 0. 1 plus negative 1 is equal to 0, so that works. And then lastly, I'm going to test 270. So sine of 270, 1 plus cosine of 270. Sine of 270 is negative 1. 1 plus 0 does not equal negative 1. So 270 in this case is extraneous. And my solutions are the two numbers there, 90 and 180.